Hello, this is first in a series on modular arithmetic. This is just basic definitions of what is it, what does it mean to do arithmetic modular a number. So first we have to fix such a number. It is a natural number, an integer bigger than 0. And then it allows us to group integers in big chunks. So we say that two integers are equivalent, congruent, modular n. So that is the definition of this relation of congruence. I will write just n in brackets, not mod n as usual. It is defined to be the following relation, that a and b are congruent if and only if n divides the difference of a and b, which spelled out means that there is some other integer, say v, such that a minus b is equal to n times this v. The basis of modular arithmetic is this facts, which have to be checked using the definition. So the very first fact, zero level fact, is this congruence is an equivalence relation. That is that statement consists of three parts, three basic axioms for equivalence relation. They have to be checked using the definition of this relation, and it is very straightforward. After you do that, you can be sure that the whole set of integers is separated into congruence classes, and the notation for these congruence classes, I'll be using this integers sub this modulus n. So these are congruence, a set of modular n. And the other two facts, which I'll group together, they will make this set to have its own arithmetic operations. The arithmetic operations will be really coming from the operations on integers. So here are the facts. Assume that we have two congruent pairs, mod n. A and b are congruent to each other, and c and d again related by this congruence. Then we can have two conclusions. So the first one, if we take the sums of a and c and b and d, then we can be sure that they will be congruent as well, mod n. And the same for products. The product of a and c and the product of b and d will also be congruent, mod n. So that is always inevitable in these assumptions. That in plain was saying that doesn't matter what we take in our congruence class. Usually it is a remainder, but we can do something else. Whatever we take in the congruence class of a number, as long as it's in the congruence class, it doesn't matter how we choose it. And the same for another class. Computing the sum will be the same as any other way, under any other choice. And computing the product will also not be affected by our choices of representatives in class. So this is saying that you could do arithmetic operations on classes without fear. You will stay inside a given class after performing an arithmetic operation. This makes the set, equips it rather with addition. Subtraction, of course, will follow automatically, and multiplication. Not always division. Let's look at which numbers mod n are invertible. So finding inverse to a given number a is solving this equation. The product of a with this unknown is supposed to be 1. That's the key. That's the definition of the inverse. Let's just look at our meaning which we had under this notation and see what it amounts to. So the congruence is the same as saying that n divides the difference. Let me just spell it out in the equation form. So there's something I can multiply by to make it equal to the difference, say, of 1 and ax. And let me rewrite, maybe I will call it not v but y. And let me rewrite this equation in a kind of better form, putting ax on the left. I will have this equation. X and y are my unknowns. They are to be found in integers. That is known to us as a linear Diophantine equation, and we know when it is solvable if and only if condition, a criterion, is that the greatest common divisor of a and n has to be 1 for such to have a solution. Well, necessarily, because greatest common divisor divides the left hand side and should divide the right hand side, but conversely it follows from the Euclid's algorithm. So this is the condition for a to be invertible mod n. A is invertible modular n if and only if this happens. The greatest common divisor is equal to 1. So that's the necessary and sufficient condition for a given number to have the inverse. In particular, when n is a prime, any number which is not divisible by that prime will be co-prime to it, and so all numbers modular prime which are not 0 class will be invertible. So let me look at one such prime and look at the table of inverses for all non-zero residues mod 5. 1, 2, 3 and 4. Then 1 is always inverted by itself. After all, just 1 times 1 is equal to 1. And 4 is as good as negative 1. So that is the case where going into choosing different representatives in the congruence class is better, is more revealing. Negative 1 is its own inverse as well, so 4 is also its own inverse. Well, we could check it directly. 4 times 4 is 16, which is congruent to 1 mod 5. But it will work modular any number n. So what is left is to find inverses for 2 and for 3. Well, it's actually enough to find inverse for 1, and then the other will be automatically settled. The inverse will be determined. So for 2, if we multiply it by itself, well, we have 4, which is not 1. But if we multiply 2 with 3, we will have 6, which is congruent to 1. So the inverse of 2 is 3. And vice versa, inverses come in pairs. So we completed the table of inverses, module 5. See you later with more.